Okay, so the reason why we're discussing how to calculate truth functions for individual compound statements is that that is part of the piece of that we'll need to have in order to calculate the validity of an entire argument using truth tables. Again, this is what we've been sort of building up to up until this point. We're trying to figure out whether or not an argument, a deductive argument, is valid or invalid. Okay. So as we were discussing last week, if you know just one set of truth values, you may be, for that set of truth values, be able to determine whether it's a valid or invalid argument. But you ultimately you want to know if the form of the argument will ever output an invalid combination of truth values. Okay? So that's why we need to be able to calculate every possible truth value of a particular form of an argument in order to figure out if that argument form is valid or invalid. Again, validity is specifically, by definition, the idea that a deductive argument, it can never be the case that a deductive argument has all true premises and a false conclusion. So if you find a possible combination of truth values where all the premises are true and the conclusion is false, then you know that that particular form of the argument is an invalid form. Okay? And it will not be a good form for a deductive argument. So part of this is that we need to figure out how we can start these truth tables and figure out how to put them together in order to use them to determine validity. So consider the following argument here, so with our truth tables here. Say you have an argument like, if the cat is hungry, then it will meow at the door. That's your first premise. The cat is hungry. So it will meow at the door. All right. So the question is this a valid form of an argument? And again, it doesn't really matter in the end, when we're talking about deduction here, what specific simple statements we're sticking into this form. We're trying to determine whether or not the form is itself valid or invalid. And so eventually we want to extract all of the content of the statements and replace them with, again, a singular letter. So we want to try to figure out if what we have here is a valid form of an argument. So in order to do that, again, we need to begin by extracting or getting rid of, the statements here. So we'll say the cat's hungry, so we'll say H for hungry. Meow at the door, so we'll say M. Again, we have H for cat is hungry, and M for the cat meows at the door. Again, we want to know what would happen in every combination of truth values with this form of argument. When we want to know if there is any combination of truth values, where perhaps M is true, H is true, what would that output an invalid argument, a combination of truth values or not? So we need to figure out how to do that. So in order to do that, we need to sort of get this argument down to its propositional form. All right. So sort of put together what is put in words here. We would say something like, if the cat is hungry, then horseshoe will meow at the door. The cat is hungry, so therefore the cat will meow at the door. Okay, so that's our basic argument form. And our question is this a valid or an invalid argument? So in order to do that, we got to basically do what we've done before with the truth functions and determine the truth value of each and one individual part of the argument, of all the each premise and the conclusion. So the way that we would do that is, the first step is that we need to make sure we know the number of truth combinations that we need to have within our truth table. So in your book, it tells you that you take 2 times n, where n is equal to the number of letters in the argument. That's a mistake on the part of the book. The formula that you need to use in order to determine the number of rows that are going to be on your truth table, the number of different combinations, is you need to take 2 to the nth power, where n is equal, again, to the number of letters in the argument. All right, so we can see here that we have 2 letters in this whole argument, so we're going to have 4 rows here. And so the next step when you're constructing a truth table here is it's going to look like one of those truth tables for the individual operators that we were talking about earlier. The first thing you're going to do is you're going to create a column for each individual letter, okay? And then you're going to put in a column for each individual premise and the conclusion. So H horseshoe M, H, and then I usually put in a double bar to indicate that what follows is the conclusion, M. All right. So we've already said that our truth table is going to have 4 rows to it because of this formula. So the next thing we have to do is we have to try to figure out what are the different combinations of truth values. Well, in order to do that, you need to take the number of rows and divide it by half for the first column, for just the first column. So if there are 4 rows, then we divide that by 2, and we're going to know that in this first column we need 2 trues and 2 falses. In order to determine the configuration of truth values for the second atomic sentence, you need to then take the number in each combination of truth values in the first column and divide that by half. So basically, you're going to say, since they came in couples here, you're going to go 2 divided by 2, which is just going to give you 1, which means that you're just going to alternate in this last row, or excuse me, last column, the truth values. And the last column, the last letter in your truth table will always, the configuration will always look like this. It will always be an alternation of true, false, true, false. Okay. All right. So then the next step when we're using our truth tables, we just, for each row, plug in the relevant truth values. Okay, so we know in this first row that both letters are true, so let's just go ahead and plug that in. Right? Okay. And we'll do that for each row here. Okay. Now, these columns here are pretty much all figured out, but we still have one more step in this first one because we do have an operator. It's not just a single letter. So what I often do in order to keep this neat, because believe me, these truth tables can get really long and really complicated in each particular column. So what I do is my main operator, I always box off that column. So I know that this is the final value for this whole entire premise or conclusion. Okay? So again, thinking back to our truth tables, and this is why those truth tables for the individual operators are so important, we would say here that we know, again, remembering the truth table for the conditional, for the horseshoe, we know that if there's true, horseshoe, true, that's going to be true. And we also know then that if it's true, horseshoe, F, from the table for the horseshoe, we know that that's the only time in which the whole conditional is going to be false. And so then therefore, every other case, F, horseshoe, true, T is going to be true, and F, horseshoe, F is going to be true. So here, in this little boxed off area, is going to be the final value for this premise, H, horseshoe, M. So the final step that we take in terms of determining validity is that we look at each row and see if we have a case where each premise is true and the conclusion is false. Okay. So to sort of make this simple, just look at the rows in which the conclusion is false. So we can see here, okay, here on second row 2, M is false, the conclusion is false. Well, are all the premises true in this row? true, false, nope, that one's okay. And then we have this last row where M is false, so our premise is true. Nope, this premise is going to be false. So because we have no case in which every premise is true on our one row and the conclusion is false, then because there is none whatsoever, we can say that this argument here is a valid argument. It has a valid form.